just want to keep the energy up.
Hi there, everyone. Can everybody hear me okay? I usually don't use a microphone when I give talks. Can everybody hear me in the back? Thumbs up, down, no? Yeah, okay. So hello, everyone. My name's Andrew. I'm just going to use the keys. How does this thing work? Oh.
Like this, you press the down button to go to the next slide. It's not connected. One moment, please.
Meanwhile, my name's Andrew. I'm actually an undergraduate in the Department of Linguistics, so I'm not actually in Baskin, but my research is on the relations between formal syntactic structure and studying semantic meaning with logical tools. I'm very excited to be able to talk with you all in brief about how we can leverage statistical modeling to be able to capture things like linguistic meaning in the form of sentiment analysis, okay? And just as a brief start here, even if you've never heard of the word or the phrase rather, sentiment analysis, can somebody give me a breakdown of maybe what that means from a non-technical perspective? Sentiment analysis. Even if you've never heard the phrase before, does somebody want to let me know what maybe you think sentiment analysis might mean? And I'll also let the other Sky team members chime in if they want. Yes, yeah. Okay. Speak a little bit more to that. What do you mean? Okay, exactly. And that's something that we're going to explore today. And we have to explore it from a more formal perspective, right? If I talk about the word sentiment, the first thing that comes to mind, at least for me, is, okay, how do I feel about this particular situation? Maybe it's a book, maybe it's a song. What kind of sentiment is this giving off? Or how am I interpreting what I'm hearing or seeing? But we have to be able to apply formal tools to that. So first, I'll start off with maybe a more common example. Oh. Okay. Let's start with a simple scenario. Let's say we have a bag of marbles, and there are 10 marbles in 4 colors, if I recall. 3 red, 4 blue, 2 green, and the last one's purple. How would we go about determining what the likelihood is to pull that last purple marble from there? There's only one in there. Yeah. Okay, and how did you come to that percent, by the way? Okay, and by that logic, what would be the percent likelihood for pulling a green marble? 20%. Exactly. Whoops. This is unintuitive. Okay, so this forms the modern foundation of conditional probability. In other words, we commonly refer to it as Bayesian statistics. And it all starts with Thomas Bayes, who was a philosopher and mathematician in England in 1761, which is when he died, but he published posthumously the sort of foundation for actually what even the Department of Statistics here at UC Santa Cruz specializes in, which is how do we account for the probability of something given that something else has already happened, right? So how does one state or one event influence the outcome of the next one? So just so we're all on the same page in terms of notation here, can somebody give me a breakdown of what this notation is that we're seeing here on the left side of the equation symbol, by the way? Yeah, in the back. Can you, do I dare ask, can you maybe give me a slight example of what exactly that means? Just an example. Okay, yeah. It's, I always think of it, it's kind of like a problem or like an assignment that you get as homework. Here are all your givens, calculate this, right? So in order to calculate the probability of some event A, given some other event having happened B, we need three things. So we need the probability of A, the probability of B, and then the probability of B given A, so the flip of that. So if we want to reapply this to our original example, let's say we still have the same number of marbles, same color proportions, but instead, what's the likelihood of pulling a red marble without putting it back into the marble bag and then pulling the purple one like before? It's a little bit more complicated. And you can even try calculating it if you'd like. But let's recall our equation here and how we can apply that to our current example. Yeah.
I can't really do this.
Back checkers? I don't think, okay.
Yeah.
Yeah, I was looking for 130. So, and can you walk us through how you got to that answer, by the way?
Yes. So the chances of getting a red are 3 out of 10. Right?
Yep.
And then if you only have 9 marbles and one of them is purple, then that should be a chance of 1 out of 9, right? So if you just multiply 3/10 over 1/9, you get 3 over 90 or 1 over 30.
Okay, exactly. So what we're getting at here is a method of describing our environment, not based on sort of things happening where the environment remains the same after each step or each event, perhaps, but rather we're doing something here like selection or sampling without replacement, we call that, okay? So we get to now, instead of there being 10 marbles, we're actually left with just 9 because we're not putting the red one back into the bag, okay? So if we want to extrapolate this to calculating likelihood on a broader scale, how do you think we'd go about finding the probability of 2 unrelated sequential events more broadly? So let's think about what we've already done, right? Pulling marbles from a bag, 2 different events. If we have to calculate this, how do you think we'd go about this? Yeah. Okay, what's the intuition for that? Okay, exactly. So we would multiply our probabilities, and it's like pulling a marble from a bag or rolling a set of dice or something like that. And we can think about it more broadly in terms of, what if we don't just have 2 events? We roll 1 die and then another one, 2 sequential unrelated events. What if we have an arbitrarily large number of events? And that's where we can calculate this in terms of the fancy notation that we see here, but it's really much more simple than it looks. Can somebody maybe give us a breakdown of what this notation means, this sort of big, ugly math here? Yeah. Okay. So what's more commonly seen is with sort of sigma notation, where it's a big, I don't even know how to describe it, but the sigma letter. And that's with summation or addition multiple times over for however many variables or things that we're trying to calculate. And so this is just with multiplication instead, for that exact reason, as we pointed out earlier with dice. But if we're considering with arbitrarily large numbers of events, might we start stumbling into a problem here? I mean, if we think about it in terms of practical scale, if we're running an enterprise program that for some reason is calculating probability, we're going to have to do a lot of calculation. And there might be many different events happening one after the other that we need to account for. So if we're multiplying our probabilities over and over again, Jonathan, if you want to take me back to the previous formula, what's going to happen to our end result the more probabilities we add onto this equation, or multiply onto this equation, perhaps? Yeah. It would. And what makes you think that, by the way? Exactly. And this is exactly the problem that a company can run into if you're thinking about running it in terms of a business startup or something like that, or even just doing calculations, is that when you start having too many probabilities, too many events that you need to consider, or maybe if the probabilities just start getting really, really small, you end up with something called underflow. I believe that's called underflow. So I'm sure many of us have come across the term overflow, maybe or maybe not from Stack Overflow. Can we start by somebody explaining maybe what's overflow? What do we think overflow is in terms of a computer program, so to speak? Yeah. Yeah, so it's like when we're dealing with literally too big a number, too big a calculation, and it ends up being a real problem for our computation and our system at hand. So that's why if you end up taking an algorithms course or even just an introductory computer programming class, you end up having to think really critically once you start learning the foundations of a programming language or something. How do we account for time and space complexity in our computer programs, and how do we optimize those? So we have some various solutions, these kinds of things. So we can start by not taking the product of taking sort of the product of P of X, but we can try the summation of the log base Y of P of X. Now, why would logarithmic computation perhaps be a better alternative to what we had earlier when we're thinking of large scale things? This might be a tough question to answer. Yeah. Jonathan?
This is a two-part thing. There's two benefits to doing log probabilities. So for one, if you can go back to the old equation, we're working in summation. So instead of working with multiplication here, where we're going to be multiplying really small things again and again and again and getting an increasingly smaller number, think multiplying 1/100th by 1/100th, you're getting 1/10,000th. We're instead adding those values together. Additionally, if you go back to the next thing, probabilities are always valued between 0 and 1. You can't be more than 100% likely, and you can't be less than 0% likely. So the very nice thing about this is that the range of those values when represented as logarithms is a small negative number, and we can just keep adding those together and getting an increasingly bigger number. So we avoid underflow, and we don't get just complicated multiplication. So twofold.
Let's just take a step back. What's
Right. Underflow, in this case, is the opposite of overflow. More or less what we're going to be worrying about is instead of the number getting too big, by continually dividing out a number, again, let's assume we're doing 1/100th times 1/100th, there's a finite small end of what we can keep track of. Let's say that that's like 1/1 billionth or something like that. At some point, you're going to hit that value. And once you get underneath that, there's not enough precision in your storage. You're going to literally run out of space in order to keep track of the decimal, and your computer is going to round it off. A lot of the time, you'll see this as a floating point error. For example, if you're representing something like 1/2 or 1/4, you're going to have an exact value because it's a multiple of 2, even though it's to like a negative power instead of a positive one. But if you try and represent 1/3 as a floating point number, if you print it out like using Python or something, you're going to see imprecision as you get closer to the end. You're going to have 0.333167 or something like that. And that's not very useful. You end up losing precision over time, and it's the same effect. So By doing this, while yes, we do keep a lot of the error that's associated with floating point, we never lose our value completely, and it's a much less lossy process. Does that make sense for everyone so far? Perfect. Back to Andrew.
So that's one solution. We also have another one that looks, dare I say, even more complicated. And that's if we wanted to construct a classifier based on naive Bayesian analysis that we just sort of got introduced to earlier. And just so we're, again, all on the same page about notation here, does somebody want to give me a breakdown of what at least argmax means? This isn't something that I was, for instance, exposed to in high school, is what in the world does argmax mean? But what does that apply to in terms of what we're working with right now? Yeah. Okay, so see Jonathan, maybe not so satisfied there, but I'll say, if I can describe it in short, we're trying to find the maximum value of an expression given a variable. Did I switch that around?
Looking to maximize the prediction based on. So the classifier in this case, whatever is the most likely chain of events. Oh, thank you. Whatever's the most likely chain of events is what we're predicting. So if you have, like, for example, two different events, say we're going to be going back to the marbles. If we're going to be pulling out one green and then one red, versus one green and one purple, the odds that we're pulling out one green and one red is better. So that if those are the two decisions in this case, the first one is what we're classifying as. The argmax just means whichever one is the greatest, most likely thing to occur, whichever one has the bigger value, classify it as that. That's what's happening. And it's just a naive way of assigning what's going to happen.
If I could ask you one last question, Jonathan, is why do we call it naive Bayes classifier? We could have called it some ugly Greek letter or something.
Right. It's naive because that's the probability that we're working with. We're working with literally just counting the amount of times each event occurs. So even though it's represented as a probability here, if I use the laser pointer, as a conditional probability, we're conditioning on the class. So for example, if you're looking at all events that happen on a cloudy day, that's the class of events that we're looking at. So if it's a cloudy day, we're considering it. If it's not, it doesn't belong to the class, so we can ignore it. It's a naive probability in this sense, because we're just counting up the amount of times each event occurs in that. So the amount of times that you see a red ball or an oak tree or whatever, given that it's a cloudy day, that's what you use to count up and assume this probability at the end of the day. So it's naive because you're not doing conditional probabilities. It is literally just using your fingers and counting.
Okay, so that was a lot of abstract math. Let's try and apply it perhaps to an example here. Let's try and probe our initial intuitions from earlier about what we consider sort of gathering a personal sentiment about something to be. And can somebody maybe provide us some insight onto what the general sentiment you're getting from the data sentences we have on these slides might be? What's your sentiment that you're getting from them? Yeah. Okay, let's go through each one by one, and then we'll talk about it further from there. Do you understand? So like, what's your intuition for the first sentence? Okay, well, let's take a step back from positive, negative. How do you think, so let's say this is like a movie review or something. And people are getting interviewed after seeing the premiere movie of whatever's debuting for that weekend. And they say on camera, that movie was really terrific. What is that giving you in terms of sentiment or intuition? Exactly. And so, okay, let's transition to the second one. What would be your intuition if you heard that after a big cinema blockbuster? And if we go continue down the board, we can continue to understand this in terms of really just two values like you brought up earlier, where it's just positive and negative, because once we're working with large amounts of data, maybe it would be a little bit more complicated than we'd like to at this point to be able to consider how can one sentence be more positive than the other. Let's create categories based on that. We're just going to partition in the middle and say positive and negative for now, okay? And I also want to ask, even if people weren't saying it, so you don't have to put emphasis, that movie was really terrific. And let's ignore the possibility that people are being sarcastic, for instance. What sort of influence your decision to consider one sentence versus the other in terms of this one's really positive, this one's really negative? Okay, okay. Which ones, maybe? Yeah, so the kinds of adjectives or nominals that we're using, and in general, the more that we're using them, perhaps we're trying to convey a stronger meaning than if we didn't in the first place, okay? So from our perspectives, if we want to construct maybe a computer program, or we want to conduct some sort of probability analysis, we can divvy up these in terms of classes, and then sort of akin to what we just talked about, we can consider which words show up and how many times in which class, okay? And we can end up trying to sort of categorize them so we have lots of data to work with as a start, okay? So for instance, the word terrific showed up in the positive sort of sentences as opposed to the negative ones, okay? And we can construct probabilities with those based on some of the equations that we've already discussed. So in other words, what's the likelihood of this or that, given the words showing up in the classes and their frequency, okay? So what if we're fronted or confronted with a new sentence, okay? What a terrific movie, exclamation mark. How would we categorize this sentence? Let's say we're a computer program. How do you think we would classify this sentence? There are only two options. In the back, yeah. Okay, so we take a look at the words in the sentence. Let me just make sure I understand. We take a look at the new sentence, the words and things inside the sentence, and compare it with what we've already had. Maybe this is a training set or something like that. And we can consider, we can make a judgment call about which one this probably falls into. Did I get that right? Okay. What if I just slightly change the sentence? So pay attention here. What did I change? Yeah. Okay. Well, I mean, for us humans, it certainly feels like it's somehow less enthusiastic. And maybe if the people were talking, it'd be, what a terrific movie versus what a terrific movie, right? So there's an intonation difference. But even if we're just looking at the words here, if we are the computer program, we actually aren't quite sure how to classify it. Why might that be? Yeah. Let's think of it in terms of just our table here. We're a very simple computer program, and our job in life is to construct probabilities, okay, and classify sentences based on them. We'd like to say that our human side, we'd like to say that the sentence is sort of positive, especially with the word terrific there. But how many times does, for instance, the period punctuation show up as a positive sentence or in a positive sentence? You raising your hand in the back there? Do you want to answer? No. Okay, and how might that influence our future results about how we're classifying sentences? Okay, are we getting the right intuition here? I think so. Okay. So we have a broader problem here, and we're sort of getting a little bit of an understanding of it. But what happens if we come across new data and the new words, or we can include punctuation here, they aren't in what we can call our training data or what we've previously modeled our analyses on? We come across something new, right? You can think of it like if you, even just as a human, come across a character or a symbol in some English sentence that is not from any language, it's totally made up. You're not really sure how to interpret it unless it looks very similar to some other letter, in which case you make a judgment call there, right? So we have a few solutions for these as well. So we can try considering, okay, that new funky symbol we just came across in our sentence where we recognize everything else, we don't understand this. Let's just put that in a box. And we come across another one, let's do that too. And so we can create an unknown, which is sort of a lump sum of everything that we've come across that has low occurrences or no occurrences at all, just so we have that in the back pocket, but doesn't actually result in that sort of unknown classification that we just had there from the computer program's perspective. And as a drawback here, we start to see more broadly the problem of precision, kind of like with underflow and overflow that we just discussed. If we're literally not considering pieces of data in our classifications, we're probably not going to make the most accurate assumptions at scale. Do we get that intuition here? And why might that be, by the way? How does that influence perhaps what we're trying to accomplish here, and that we're classifying sentences based on their sentiment? What are some applicational problems of this? Let me take a step back. What are we training our probabilities on? Words, right? What language? English. And what if we want to scale our program or software or movie review system and we want to consider maybe other characters? What's going to happen if somebody's, so let's say this is by typing or writing, what if it's in a different language? What's going to happen? It wouldn't work. And why might that be, by the way? If you could speak a little bit more to that. It's dependent on what we've already provided to the computer program to be able to consider, right? And it'll just treat that character, even if it's just the letter A with an accent on it, it's going to treat it as an unknown character, and it's going to lump it together, which might be a serious problem for people who want to conduct movie reviews cross-linguistically as well. We can also do something a little bit more mathy, and I believe that's called little n or just n smoothing. And that's where we can add n to every sample that we grab before calculating the probability of it. And when we do calculate that probability, we can add n times the size of the vocabulary to the denominator. And I have to ask, what's the vocabulary that we're working with here, by the way? How are we constructing our vocabulary here, so to speak? Yeah. The distinct input words is sort of what we're working with here. And you might hear this as Laplace smoothing. Maybe it has another pronunciation, Laplace smoothing. Okay, so with that in mind, let's try and actually apply this ourselves. We're going to be doing this in Python like usual. But just so we have an idea of what we're working with here, y'all can try this out, okay?
All right. As a reminder, clone the notebook, This time it'll work, I promise. We didn't mess it up this time. We're doing something else. We're not loading it in the same hacky way that we did last time. We're using something from a library. So Google can't go and mess with our code anymore. But yeah, make a copy. You're gonna want to keep your changes for this. A lot of it's already filled out, so we're just gonna walk through it, and then you have an opportunity to experiment with things at the end. So give you a minute, and then we'll get that opened up.
Once you guys have it open, can you guys give us a thumbs up? Word.
This is also where we're ending the recording. So good luck to the people who are doing this later.